Good afternoon. Good afternoon. So today we will look at bypassing and EHRs. So EHR is a new thing which you haven't seen so far in Bluespec, though you may have been implicitly using it because we have given you modules which could only be put together using EHRs. But today it will get demystified and you can write your own. You can use EHRs and produce more stuff. Right, so bypassing, it's a big deal which has been emphasized to you in lectures by Silvina and Daniel. At a very high level, it's really an idea so that we can reduce the number of stalls. Something that takes multiple cycles can be done in one cycle if we can provide some way of connecting the producer of a value with the consumer of the value. So essentially, bypass, as the word implies, is providing a path, an extra path. So for example, normally you will write back into the register file and decode stage tries to read it. So that's the normal path, and a bypass essentially means that you're going to provide an extra path which bypasses the register file. So as the value is being produced, you can use it in the decode, and if you can do that, then it's going to save the cycle of storing it in the register file and using it later, right? Now there are a couple of things which are just well known, and yet it's hard to measure unless you have the right tools, unless you do synthesis of your design. And one of them is the benefits of bypassing at some level are very obvious to you. You'll be able to see, oh yeah, it should eliminate a cycle here, stall there, etc. But what is much harder to estimate is what impact it has on the clock cycle. Because bypass, by its very definition, introducing new combinational paths in your circuit, right, in your design. And any time you introduce new combinational paths, there is always a chance that that path suddenly becomes a critical path, and therefore your clock period may get larger, have to be larger in order to accommodate this bypassing logic. And this thing is something where, you know, intuition really is very hard to quantify without proper tools. So we'll show you some very simple examples of this. The next question is that bypassing is a good idea, but there is no such thing as a free lunch, so there is some cost associated with it in terms of area, in terms of clock periods perhaps. And then, you know, should I do it or should I not do it? So that depends very much on how frequently you expect the bypass to be used. If it's used often, absolutely, but if it's used rarely, then its overall impact on the performance may be minimal. So this is something else where we can do lots of measurements on the kind of programs we'll be running or the hardware you're designing, how much impact will bypass have. And this goes beyond hardware. It becomes an issue about what kind of software is being run on top of your processor. Now when it comes to bypassing in Bluespec, you're not going to find yourself connecting this point to that point combinationally. It doesn't work like that, right? So there's a different higher level view of bypassing, right? So you think of it in terms of reducing the number of cycles it takes to execute two conflicting rules or methods. Okay, so let me illustrate, or let me ask you questions. So suppose I want to build a FIFO, right, where I want to be able to NQ even though FIFO is full, because concurrently somebody is going to be DQing it. Now obviously for correctness, what you want is if nobody's DQing it, then it behaves like a full FIFO. You can't do an NQ at that point. On the other hand, if you could detect that, oh, somebody is actually going to DQ at this time, then you can also NQ. So it looks like as if you NQ'd in a full FIFO. So this is a slightly different way of thinking about, you know, the concurrent methods we have had so far, where we just said, oh, this NQ and DQ can't be done together because there's a conflict of some sort, right? They're writing the same register or something like that. But there is a reason why we want to go beyond that. Here is another example which you had seen earlier. So there are two rules here, RA and RB, and you can see quickly that they conflict with each other. Why? Because both of them, first one writes in X and the next one writes in Y, and the first one reads Y and the next one reads X. So there is sort of a cyclic dependency, and these rules conflict because you have to schedule them one by one. But you can ask the question, what will happen if I really wanted to execute them in the same cycle? What is preventing me from executing them in the same cycle? So what you somehow want is to communicate this value of X from rule RA to RB, right? In the same cycle if possible, as opposed to waiting for it to go into the register and then coming back. You should have a bypass for register X. And if you can do that somehow, then it may be possible to execute these rules together. And if you execute them together, then it will behave as if rule RA happened before rule RB. So I'm giving you very high level issues here, where I have a very clear goal, what I want to do. And now the question is, we'll discover very soon that the only solution to these things is introduction of bypasses. So we will also introduce bypasses in a very different way, at a significantly higher level than it's done in traditional digital design, right? And these kinds of designs that I'm mentioning on this slide are not possible in the subset of Bluespec you have seen so far. Okay, so why is that? Limitations of registers, if you want, because that's the basic abstraction on which the whole thing is built up in Bluespec. Okay, so when you use registers for communication, right, in the same atomic action, certain kinds of communications are just not possible. So for example, if you're writing into that registers, you can't read it in the same cycle, you read it in the next cycle. So what that does is that two methods can't communicate, as you just saw, between RA and RB, because X is being written here, and to preserve the semantics, I want this X to be visible here. Well, then I have to wait until the next cycle. Okay, so if you could, if there is a desire that two methods communicate with each other in the same clock cycle, in the same atomic action, then something is needed, because registers are not going to let you do it. Similar issue arises between two rules and two methods, and between a rule and a method. So in all these things, if a register is being set, it can be read by the other entity only in the next cycle. And this is what we want to get over. We want to, see how to solve this problem. And actually there are quite a few solutions, and I'm not going to give you the history of them. And it depends in the eye of the beholder, but some of them are pretty ugly. They will turn Bluespec from a high level language into a very low level language. So this is the solution that I like best, which is called EHRs. EHR stands for Ephemeral History Register. A mouthful of a name, and I won't go into why we named it like that, but EHRs is it, a primitive element to design modules with concurrent methods. So in other words, what I'm going to do is, until now you had a Bluespec with registers, now you're going to have a Bluespec with registers and EHRs, though an EHR can also be used as a register, ordinary register. So EHR in some sense subsumes the register. But let's not mix them up. I mean, when we use EHRs, I want to use it explicitly so that you know what you're doing with this. Okay, so this idea was introduced by Don Rosenband in his thesis, and there are many, many interesting aspects of that work. But just imagine I'm designing a module, and what is my register with enable? That's what I have shown you on this slide, right? You have a flip-flop, and you keep feeding it back. So if there is a new write coming in, it's enabled, then the new value gets captured, otherwise it doesn't change its value. So that's what reads and writes behave like in an ordinary register. So this is the normal behavior, and if you do them in parallel, it behaves as if read happened and only after that write happened, because the effect of write can only be seen in the next cycle. So far so good? All right, so now I'm going to embellish this a bit, extend this a bit. How about this? Suppose I also provide another port on my register, which takes this output and puts it out. So what is R1 now? How does R1 behave? It's actually going to read the value if the new value is going to be written. In other words, if you have, R1 returns the current state if W0 is not enabled. So if nothing is enabled, it's just like R0. On the other hand, if W0 is enabled, something he's trying to write into this register, then R1 will see that value. It's being bypassed. It's a bypass path. You can see it, even though the register, anybody who's reading R0 will only see it in the next cycle. So here is a register element where I'm giving you both. I'm giving you the normal read and I'm giving you the bypass read from it. So that's half the idea of EHR. The second idea is that we are also going to give you another write which is prioritized, right? So if you have W0 and W1 and both are enabled, then I want the system to behave as if W1 is the one I wanted. So even with the same clock cycle, if you want to do W0 and W1, I want W1 to prevail, and this can be done simply by this circuit. So I take something that is coming from W1, and then if W0, and if W1 was also enabled, we will select that using this enable, and that is the value that will be stored in your register. And if you do it like that, then it's very clear that W0 comes before W1, though there is no guarantee that either will be enabled. So you have to understand the behavior of this circuit. When neither W0 and W1 is enabled, somebody tell me, what do reads look like in that case?
You just get R0. Right?
It'll be the old value, whatever was stored in register beforehand. That's what you will see. Suppose W1 is enabled, then what will happen? I keep going. No, I keep jumping. Suppose W0 is enabled. What will you see?
The new value at other one?
So R0 will still see the old value. R1 will see the new value that is coming in. And what will I see in the next cycle?
Same.
The value that you just wrote, right? W0 is what will be visible in the next cycle. Now tell me what will happen if W0 is not enabled, but W1 is enabled. W0 is not enabled, but W1 is enabled. Yes?
We'll get the old value from the register.
Yes, and what will R1 see?
R1 will see the old value from the register.
Very good. So both of them will see old value, but the value that will be stored in the register is the new one, right? Is the W1 value that you're writing. And now it's an easy extension. Suppose both of them are enabled. Tell me what will happen. Yep.
So R0 will still see the old value, but R1 will see the new W0, and then W1 will write to R0 after the next cycle.
So in the next cycle, I'll see W1. Fantastic. So everybody got it. So functioning of this is straightforward. But like in most things in Bluespec, we don't want to think in terms of low-level circuits. We want to think in terms of some higher-level thing, and that will be an EHR declaration. So anytime you do an EHR, you're going to get this 4-ported device, 2 read ports and 2 write ports with its own behavior. So we like to capture these things in terms of conflict matrix. Just a reminder, the conflict matrix for a register was simply that 2 reads, of course, don't conflict with each other, and 2 writes into the same registers, of course, conflict with each other. But if you do them simultaneously, it looks like register read happened before the write, right? So that's what is captured in this. And now based on this, I want to derive the conflict matrix for EHR. So I filled out the part which is just like the register. right? I mean, if you're just focusing on W zeros and R zeros, it's just like the old stuff. All right, so now tell me, what should go into EHR.R1, right? If you are writing something at that point. So it'll look like as if the write happened and then the read R1 happened, right? Because by design, that's the bypass. You're seeing it, come after that. And the reads, of course, remain conflict free. And these things always have a duality. So if you fill these things, then you can fill out the diagonally opposite entries in a similar way. All right, now what about, does this make sense? By definition, W0 comes before W1. You have seen the circuit, right? So if you are trying to do W0 and W1 in the same cycle, it will behave as if W0 didn't happen. You will just read the W1 value as far as storing the value in the register is concerned. So that's why you have that. And again, by symmetry, you will have this over here. Now, what about R0 and W1? So you are reading R0 and somebody is writing in W1.
It'll be a bigger than sign because we get the new value that's being written.
It will be that you will see it in the next cycle. You are not seeing it right now, right? Because you only see what was being written in I mean, this is I was talking, how do I should be pointing, I'm looking at this entry, right? So if you are reading something here and writing in W1, you won't see it right now, right? You'll see it only in the next cycle, so that's why it's less than that. All right? This is obvious that R1s are conflict free, and two people writing into W1s will definitely be a conflict. It's like the same double use of a port, never allowed, and you can argue out what this entry should be. So, it may take something, but given that diagram and your understanding, you should be able to fill this out. So when you design this circuit, this is the kind of conflict matrix that will be generated, but I do not recommend you design this circuit because this cannot be designed by you. It requires some very low-level hacking inside Bluespec. So from our point of view, we're just going to use EHR as a primitive. We're going to use registers, just as we have used registers, now we're going to use EHRs also as a primitive. And now what I'm going to do is actually do some practice. Let's design a few things using EHRs. So what we're going to do is design a pipeline FIFO, which allows you to NQ into a full FIFO as long as there is a simultaneous DQ going on, and we'll design a pipeline FIFO which will allow you to DQ from an empty FIFO, provided somebody is NQing at the same time. The value will slip through it and you will see it at the output. And we'll design a conflict-free FIFO, which we had done earlier, but our conflict-free FIFO had a dead cycle, right? You could do reads and writes, but then you had to wait internally for canonicalization. So from outside you couldn't tell, but from inside you'll be able to see that we can design a more efficient FIFO of this sort, where NQ, DQ do not interact with each other. They can be done concurrently. And there is no dead cycle. You can keep doing NQ and DQ every cycle in this FIFO. Okay, so what I want to show you is that whatever work you have done so far is already very useful. We can use that and transform those FIFOs in a very systematic way, right, to generate the FIFO of our desire. So let's look at this. So this is the one element FIFO from lecture 17 or even earlier, I think. And here's the conflict matrix, where, NQ, DQ can't fire together because they, mutually exclusive parts of this. So this is the one element FIFO we had earlier, very, very straightforward to write, but doesn't have, exactly the properties we want. So the question I'm asking is, can I convert it into a FIFO where NQ will happen before DQ? Or can I convert it into something where DQ will happen before NQ? In other words, can I transform this into either a pipeline FIFO or in a bypass FIFO? Okay, so let's see how does this transformation work. I have copied the code again here, and now this is the config matrix I want in this. So what is it that I want? I mean, if I want to be able to NQ in a full FIFO, then I have to know if DQ is happening, right? If DQ is happening, then I can do the NQ also. So what that is saying somehow is, if V is being written, right, by DQ, if I can communicate that information to the NQ, well, then maybe I can do something about it, right? Because ordinary registers do not allow this communication. You know, two methods cannot talk to each other except through the next cycle. I want to do it in the same cycle. Any ideas how we'll proceed with this? What is this reminiscent of? Somebody is writing into V and another method wants to read it in the same cycle. What does that remind you of? We need a bypass, right, of some sort. Okay, so let's replace this V by an EHR. So EHR, you know, I'm just dealing with two read ports, two write ports, but you can have EHRs with N ports if you want. So that's why that 2 is written here. Okay, otherwise it's just like a register, you know, its type is Boolean and it's initialized to false. Okay, so when you have this, what I'm going to do is I write in V0 in DQ and I read in the same cycle. So I'm reading the bypass path from there. How many people understand this? Okay, so what was happening in DQ, I was writing in V, right? So now I'm going to writing in V, same as writing V dot, you know, 0 in that, right? I mean, that's the first port I was writing into it. But the change I want is, in my NQ procedure, in my NQ method, I want to be able to see this right away, as opposed to the next cycle. So I want the bypassed version of it. So which is the bypassed value coming out of V? V1, right? So V, you can write in V0, V1, you can read V0 and V1. So when you write in V0 and you read V1, you're actually reading that value at the same time. Yep.
So before we had the guard for NQ as not V, and
right.
the guard for DQ as V.
Right.
So they like conflicted through the guards.
Yeah.
Do they still conflict through the guards?
We are not done yet. This is just to establish some, you know, at least we can communicate, right? So first of all, the moment you have made it in EHR, this has become an illegal program because there are V's here which are not EHR. So you make up your mind whether V is a register or V is an EHR. If V is an EHR, then all the V's have to be changed. So that's the next question. What should be the V in the DQ part when you're reading it?
V0.
It should be V0, right? Because you're seeing the current state, you know, is there space in it, you know, is there some value in it? Okay, so this has to be V0. Please ask questions because I'm seeing too many blank faces here. What have I done by doing this? Yes?
Why is that third method then V0?
Because I could give you a long-winded answer, but the first one is reading the current element. You could have defined a different first. You could have defined a first which is just going to read whatever came in, but that's not what we were trying to do. Our only goal was that we want to be able to NQ in a full FIFO. So you can experiment with that. I mean, if you wrote it as V1, you'll get a different FIFO yet. And not all of them will make sense. I mean, you'll say, how will I use that one? You know, this one has a very specific purpose in mind but you can try to design something with all kinds of funny entries in this. So what was I going to say about this? Yes. So remember, our goal in this thing is that DQ happens first and then NQ happens. Whenever you have such a clear understanding, that means anything that was going to happen first, put zeros in it everywhere. Because you want it to happen, right? You're not dependent upon anything else. So therefore in DQ, you have V0 and you're writing in V0. And you are saying NQ will happen afterwards. Right? So what does NQ do? It was reading V, so we already agreed that it should read V1 and not V0 because we want this communication. And what should happen to the V it's writing? It should be V1, right? Who's going to argue with me that that's the right answer? What happens if you do NQ and DQ simultaneously? This is a one element FIFO. It'll still be full, right? I mean, it had something in it, now it's going to get something in it again. So you want V1 to be true. So previously, what was a conflict that V was getting false and V was getting true and say, make up your mind, we have resolved that issue. We say, it can get a 0, it can get a true or a false, but in this case, V1 has priority over it, right? It has precedence. If you're writing something in V1, then that will prevail. It doesn't say that somebody is writing in V0, but if somebody is writing in V1, that's the value you're going to get the next time. So that's what happened here. And again, it's very mechanical. If you want NQ to happen after DQ, then in DQ everything is zeros, in NQ everything is ones. More questions? Okay, so basically what we have done is we're saying NQ sees DQ, V has the right value in all cases. So there are quite a few cases which you have to analyze, that NQ is being done, not being done, DQ is being done, not being done, nothing is being done, right? So in all those cases you must end up with the right value for V and D, otherwise your implementation is not correct. I'm a happy camper, so I use my ordinary FIFO, and after a while you'll get so good at it. I give you an implementation, say, what do you want? Do you want this before that? Okay. These are the things I have to change, and you'll just go and introduce EHRs and use the proper ports into your EHRs to achieve that goal. Let's do a few more exercises, okay? So let's now make a bypass FIFO. So bypass FIFO is opposite. We want in bypass FIFO to NQ to happen before DQ, right? That's like saying that I want this value to be communicated here, because if somebody is NQing, then I want to be able to read that value. I want to be able to sense that, something like this was happening, and in order to do that, I'll have to change again to this V has to be changed to VHRs, and you'll change all these values accordingly. Because if I write V0 in NQ, then DQ, when I read V1, I'm seeing the latest value. I know that somebody wrote it. But this is not a complete picture, because there is a D in this picture too. And what D do you want to see when you return D? Right? This is the D you want to see. So that means if I write in D0, down here I must be reading D1 if I want to read the same value in the first operation that I perform on it. And if you do that, that means D also has to be changed into an EHR. Are you getting the basic idea behind EHRs? That instead of introducing bypasses everywhere, we have encapsulated them in this new register element called EHR. And we will use EHRs to introduce bypasses everywhere. Yes?
Why did we switch in this case so that NQ happens before
NQ because this is a bypass FIFO as opposed to a pipeline FIFO. So in bypass FIFO, the idea is, suppose the FIFO is empty. So that means you can't DQ from it, right? On the other hand, if somebody is NQ, I could be clever and immediately pass it on. Right? So that's what the idea is, that NQ happens and then DQ will sense it. Same thing is true for first. Okay? So again, the same stuff, no double write errors, even though two people are writing, because they're writing in different ports now. And when they write in different ports, we have defined the priority that port 1 has higher priority than port 0. Very good. Okay, so this was our two-element solution, two-element FIFO, where we were successful in making NQ and DQ conflict-free. But there was this internal rule called canonicalize. So you happily did your NQ and DQ, and then there was sort of cosmic silence for a cycle, right? When internally something happened, right? It got into the right shape, and then you could do more NQs and DQs. And this was explained in this conflict diagram when I included the conflicts with canonicalization. Canonicalization was mutually exclusive with all the other methods in the system. And suppose I don't want that. Suppose I really want canonicalization to happen as soon as I'm done doing NQ and DQ, or either NQ or DQ. I want canonicalization to happen all the time and not take an extra cycle. Can we transform this program? And by now all of you know the trick. What's the refrain? Replace all registers by EHRs, right? What do you want to happen first? NQ and DQ should happen before canonicalization. And NQ and DQ are happening in parallel, so they are conflict free with each other. So they're all zeros, right? So this is what I do here. By reading zeros, what you're implying is anything you do, right, is based on the old state, whatever was in the system, because I'm not reading any bypass value. Same thing is true for the NQ part in this, right? DQ part, sorry. Everything is zeros. We could do this much before, we knew that. I mean, just using registers, NQ and DQ were going in parallel. Our only problem was canonical couldn't execute because it conflicted. So now what are we going to do to our canonicalization rule? Is just waiting for all these other methods to execute, right? And if anybody executes, they'll be writing in zero, so it's going to go and read once. It does bypassing. So this is the solution here. I have replaced everything in the canonical methods with zeros by ones. So by definition, canonicalization is seeing the updated values, right? All the values, they haven't been updated in the register yet, but we have provided extra paths, we have provided bypasses so that they can all view the values that are coming in to NQ and DQ, etc. So now this FIFO is wonderful because it's conflict free, and you can keep doing NQ and DQ every cycle in it. There is no dead cycle in the middle. Okay. Very good. Now, we can keep doing this to all kinds of modules. So we have a register file, right? And what is the normal view of a register file? That reads happen before writes. In other words, if I do simultaneous reads and writes, I read the old values from the register file, and whatever I write will be visible in the next cycle. Straightforward code to write. And now suppose, can I make it into a bypass register file so that on my reads, if you were writing in the same register, I want to see that value. So that's the idea of a bypassed register file. So it should behave as if the write happened and then reads happened. It turns out to be a pretty useful thing that we use, right? So let's try to implement this. And if we continue with this idea that we have so far, what we could do is the following. I can just declare the whole register file to be EHRs. So each element of my register file is going to be an EHR, right? And does this code make sense? I changed the declaration so that instead of instantiating registers, I'm instantiating EHRs. And then when I write, I write in, it's W0, I write in the port, but when I read from the register file, I'm reading port 1s from it. So this will automatically capture anything that was coming in and you'll be reading out. Not a difficult thing to do, but to most people this seems like an overkill, right? Because you're doing just one write and you have turned the whole register file into a, EHRs, which is a lot of logic. Is there a better way of doing it, right? Which takes much less hardware. All right, so let me give you another design for this, which we'll keep our old-fashioned register file, and we'll put some glue logic outside it, some funny logic outside it, so that the whole blob will behave like a bypass register file. Okay, so how does this work? The idea is very simply the following. Instead of directly writing into the register file, you write into a FIFO. Okay? And whenever you have to read something, instead of reading from the register file, first you try to find it in the FIFO. If the value exists, that means somebody tried to write it, you want to read that one. If you don't find it there, then you go and read it from the register file. And at your leisure better not be too long, you can move these values from the FIFO into the register file. Whenever you find time, just move it from here to there, right? Move it from register file to, from FIFO to register file. Is the high level plan clear to everyone? Yes? No? Okay, let's try it again. So I have my ordinary register file which keeps old values, right? But every time you do a write, I create a small buffer here. So new values are being written here, because I may not have had time just to go and update the register file. So whenever you do a read, before reading the register file, I just read this buffer first. Say, is there a value for register R in here? Yes, then I read that one. If not, then I go and read the register file. So that's the whole idea that is trying to be captured in that diagram that is shown up there, where RF is the ordinary register file and this whole blob will behave like a bypassed register file. Okay, so help me write this code. So what will write do? What does register write do? Sorry, register file write do in this case? It's just going to write into FIFO, right? So you have, I need all these declarations that my register file is ordinary, and I have introduced a FIFO, bypass FIFO in there. And so I'm calling this FIFO bypass, because that's where I'm keeping all the bypass values. So I have now enqueued a value into the bypass register file. That's all register write does. What does register read do? Who's going to tell me at high level? Yep.
If there's something in the FIFO, it'll read it from there. If there isn't, it'll read it from the register file.
Very good. So we go to bypass dot, I'm being fancier, I'm assuming FIFO is very big. It's really one element, so it's a very simple test. So there is no search going on per se, but if you had two elements, then you'll have to write more code, but I'm just writing it more abstractly, right? So you can search the FIFO, and if you find this value, then you will return it. Otherwise, this is what is being shown here, that if it is not in the bypass FIFO, then I go and read it from the register file. Otherwise, I just read from the bypass FIFO in this. And the second read is exactly the same because it's a two-ported register file. There is no change in that. So far, so good. So we are reading from here. We are writing into this. But somehow we have to get things into the register file too. Yes?
I wanted to ask what's the difference between a FIFO and an X-FIFO?
I'm coming to that. Okay, so that's the thing that is written at the bottom. You have your FIFOs, right, of any ilk. So this has nothing to do with bypass or not bypass. Ordinary FIFO, and now I'm going to provide you an extra function on it, search. Right? So for that, you can search on anything inside the FIFO, but generally we think of it as a key value pair being inside the FIFO. But you could have searched on any bit pattern in the value. So you define the search function when you make a searchable FIFO. And it will just go element by element and returns the value. It tells you whether it found it or not. There are many, many possible designs, but in this case it's a total overkill, because if you have a one element FIFO, you can write down all the logic yourself of the searchable FIFO. But in the library, you'll find S FIFO. So anytime you see S FIFO, that means a searchable FIFO. Okay. And then you have this move function, move rule. So what is the move rule doing? Yep.
It moves stuff from the FIFO into the register file, like every cycle when there is one.
So now I want you to take it a step further. Tell me, when does this rule have to execute?
It executes when there's something in the FIFO.
Must it execute then? Suppose I don't execute it, what will happen?
I mean, it'll write nothing.
Sorry?
It'll write nothing to the register file. It'll just be empty.
Right, so what will happen, it will try to build this bypass FIFO has to be bigger and bigger, right? If you don't ever write it. But bypass FIFO itself is fixed size, one element or something. So how will this register file behave if you don't execute that rule?
You lose a write. You lose a write.
Well, we can't afford to lose a write, right?
That's what will happen if you don't.
Exactly. So remember, in Bluespec, every method has a ready signal. Until now, the register file behaved as if the ready signal was always true. Now what will be that ready signal for the write? It will be the ready signal of the, who's going to help me here?
Bypass FIFO?
Bypass FIFO, right? So if bypass FIFO has no space left in it, says sorry, can't execute this, can't do this enqueue, that means the outer thing will stop. What I'm trying to show you here is Bluespec at some very high level remains an extremely time independent model. Right? So whenever we argue in terms of cycles, whenever we argue in terms of concurrency, it's always for performance, which is extremely important. But performance is not any more important than correctness. And whenever you argue correctness, you can see this is getting too much for me. I'm going to argue one thing at a time, right? Let's do this first, let's do that first. And that level of argument is also always valid in Bluespec. You can think of your designs regardless of how many things are happening concurrently, one at a time, one at a time. Even after EHRs, everything has a proper meaning, one rule at a time. We do not sacrifice one rule at a time semantics of Bluespec just because we have introduced bypasses in EHRs. So that's really at a deeper level, that is the invention here. Otherwise, EHRs would have been just a hack. But it's a hack with very, very good theory associated with it. You know, you're eating your cake and eat, you know, what, I missed my metaphor. But you get the point, eat your cake. Okay. Right. Okay. So we will have a register file designed this way. And now, you know, if we really want to be honest, we should go and synthesize a register file using EHRs and synthesize a register file using this stuff and see, you know, what are their properties, which takes more area, which takes, you know, which has better delay and so on. So don't take my word for it. If you want, go and synthesize both these things and you'll see the difference. Okay. Now, what I have shown you so far is actually interesting, that I can take these modules and I can derive many derivative modules, right, which have the same functionality, but they have different concurrency properties to them, which is extremely useful for me to design these systems. And this idea can be applied to many different things. I just showed you two examples, FIFOs and register file. But you can do scoreboards this way, you can do memory systems, just provide so many variants because of this, you know, because in some places in memory system, we absolutely cannot afford to lose a cycle, right, because it will be just have drastic consequences for performance. In many other places, we don't care if extra cycle gets introduced, and if you're wasting too much time with bypasses there, you're wasting time. Okay, now the good thing about such uses of EHRs is outsider doesn't have to know anything. You know, so you're an introductory class, well, you guys are very advanced, but you know, if you didn't understand EHRs and somebody says, don't worry about it, here is a module, use it. Here is a bypass FIFO, use it. Here is a bypass register file, you use it. In the rest of your design, you don't have to worry about EHRs. You can just use these modules as they are in a black box manner. So we deliver on that promise too, you know, that whenever you use these things, we do not break the black box model of use of various modules in the system. But what can happen when you use such modules is that it can affect the delay of combinational paths, because, you know, there is no free lunch. Whether I'm going through bypass FIFO or I'm introducing explicit bypass, there is a bypass at work. And anytime there is a bypass at work, you can make the combinational paths longer. And that makes things worse, right? So let me just quickly illustrate how this shows up. So you may recall this from an earlier lecture, right? So we were designing two-stage pipeline and we were trying to resolve, you know, the control hazard, you know, so we were speculating, and then we did a very good design where PC is being updated here and a PC is being updated there, and we had epochs and everything, and boom, you know, two rules conflicted because they were both writing in PC. So it turned out to be a bad design. It produced right results, but it was not any faster than multi-cycle version of it. Now, if I had taught you EHRs earlier, all of you would have said, oh, use EHRs. Why? Because we are using, you know, we are updating here and we are also updating here, which caused a conflict, and therefore these rules became conflicting with each other. Now you have this big weapon in your arsenal called EHR. What will you do?
You can have PC 1 being read to back and PC 0 being into and to execute.
Did everybody get that? Turn PC into a EHR, right? So instead of using an ordinary register, use it as an EHR, and it has two input ports, right? So I will write here, and I should be allowed to read this thing in the fetch part. And let's do that. So when I do all this, what happened? Right, so I have turned PC, and you will realize you have to do this to APAC also. So what you will find is wherever I was using PC, whenever I was writing in PC, I'm writing in PC 0 here, and I'm reading epoch 0, I'm writing in epoch 0. But in the fetch stage, because I want to see what happened later on, right, in my pipeline, I want to know right away what happened, because this is the older stuff that is happening. So there I read PC1. So you updated it in the execute stage, and we provided a bypass from this to the fetch stage, so there you can read it, what's in the what is the new value of PC that somebody wants to write. Yep.
Why are we using the 0 index in execute and 1 in fetch and not the other way around?
Who has the authority in this? Who knows who should prevail in case of, you see, remember the first one, the fetch stage, is speculating, right? So this is the thing, whatever it does should prevail, because fetch stage comes after me. It comes before, but the older instruction has the authority to update everything. So that's why this happens first, and then you will do it over there. But these are exactly the kind of questions you will have to face. And I just wanted to show you what happens when you do this. First, this last one is the one that is done using EHRs. See what happens to the number of cycles. They drop dramatically. They drop so much, because the moment you see it, wham, you go and update it, at the same time. But because there is some extra bypassing going on here, right? Indeed, the critical path became longer, and that is reflected in this bottom row here, that we were getting these kinds of timings, before for clock period, and now suddenly it went up by more than 120 picoseconds. No free lunch, right? And so therefore you have to look at the multiplication of the two things. Generally, I would say use EHRs if you're using it like this very, very carefully, because in big designs it gets harder to analyze, what's happening. So in modules, yes, because there are short bypasses going on, and we can analyze the effect. When we use it, we can plug in this module versus that module. But when you use EHRs at a higher level, then there is many other things going on in the solution. I think there are other things I could have told you, but this is more than enough I would have told you how you can use the ideas in the project, but you have that slide, so you can see it. Good, thank you.